Okay, let's pick up with our OpAmp circuits. Okay, so our ideal OpAmp circuits. Let's see. All right, so virtual short and virtual open. And then, so far we looked at OpAmps in open loop, right? Open loop gain is infinite, OpAmp by itself. Now we'll see what happens when we actually take the output and connect it back into the input. So now we have a closed loop, and there is feedback going from the output of the OpAmp. So right now it's open loop, meaning the output has no relationship or connection with the input. But now, if we take the output and connect it back to the input, either the positive or the negative, we have a closed loop. The output portion, a portion of the output is now fed back at the input, and so we term that as feedback. If the output is connected to the negative terminal or the inverting terminal, then we say it's negative feedback. If it's connected to the non-inverting terminal, we say it's positive feedback. Okay. Negative feedback inhibits the output. Okay. And there are a few things that happen due to negative feedback. And then positive feedback enhances or reinforces. And there are some responses. I mean, there are some results due to positive feedback also. So negative feedback results in a decreased sensitivity to signal variations, meaning if your input signal changes, your OpAmp response is not fast enough. Okay, so decreased sensitivity. However, it increases the bandwidth of operation, also improves the signal to noise ratio. This is particularly important, again, because noise signals will appear equally at both terminals. Okay, so we want the OpAmp to amplify the difference between the two terminals, thus eliminating the noise signals. So SNR values are higher in negative feedback. Many of the applications for an OpAmp uses the inverting configuration, meaning the output is fed back to the inverting terminal. So we use these for like amplifiers and amplification. We can create amplifiers with both negative and positive feedback, but negative feedback is far more preferable. Here, it encourages oscillation, and so it is used in oscillator circuits for signal generation. Signal generation. Okay. Negative or inverting, a real life example would be for noise cancellation. You have a audio input signal that looks like this. You invert it, so it's 180 degrees out of phase, thus resulting in zero output. Okay. So far, so good. So let's look at the first example or first circuit with negative feedback. All right, so you have an OpAmp. You take the output, feed it back into the inverting terminal. No other resistors, nothing else is in the circuit. Okay, it's simply the op amp. You're taking the output, feed it back into the inverting terminal. What happens? Well, when you provide negative feedback directly from the output, V in and V out are exactly the same. Okay, V out and V in are exactly the same. So what happens is, as V in increases, V out should also increase by the gain amount, A. However, as V out increases, then V negative here also increases. If V negative increases, that has the effect of V out being decreased, because the difference in the signal should be amplified, and in that case, V out would correspondingly decrease. This happens at an extremely fast rate. As soon as you build the circuit and you apply input signal, output is equal to V in. Okay, output becomes equal to V in. So since V out is equal to V in, we say, let's say as V in changes, V out changes correspondingly. So V out is effectively following input V in. Hence, this circuit is also known as a voltage follower. Voltage follower. Okay. One of the most common applications for this is used as a buffer or an isolation amplifier. So you would be asking, why would we need a circuit if V out is the same as V in, right? Well, this is to prevent will prevent loading effects between two circuits. And I'll show an example. So let's say we are considering a laptop charger or adapter. Okay, laptop charger or adapter. Typical laptop adapters are around 19 or 20 volts. So let's just say we choose 20 volts, right? What is the standard USB DC voltage? Anyone? It's a standard USB spec. That's why we are able to plug in a device in any USB port. 5 volts. It's 5 volts. Your desktop computers, your laptop computers, mobile phone chargers, everything is 5 volts. The current changes, but the voltage is always constant. Okay, that's a standard spec. Now you have, going on a little bit of tangent, there is USB-C power delivery, PD. USB-C PD can have multiple voltages going all the way up to like 20, 25 volts or even higher than that. Okay, and so that is the use case scenario in fast chargers, where the current is also increased and the voltage is also increased. Anyway, so let's say you want the USB DC voltage 5 volts. So if your laptop adapter is only outputting one voltage, 20 volts, what is happening inside your laptop? Well, it's splitting into multiple different pathways. From those 20 volts, we need 3.3 volts, we need 5 volts, we might need like 10 volts. Depending on the different circuit components, different voltages are required. If you're designing a USB port, and a USB port is supposed to supply 5 volts, you might have a voltage divider circuit that looks like this. And that'd be plus 20 volts being applied across that voltage divider network. The output of the resistor is 5 volts. Let's call this Vx. Okay. Now, what happens if instead of 20 volts, sorry, not 20 volts, at the output of the USB port, you connect a very low value resistor or low value load? Okay. So let's say this voltage divider network was random, 3K and 1K. Okay, 3K and 1K. If you connect load RL as 10 ohms to that 5 volt output, your circuit becomes like this. You got 3 kilo ohms, you got a 1 kilo ohm resistor right here. This is 10 ohms. Let's scroll down. So what happens when you connect a very low resistor value as load to your USB port? Exactly. Takes all the current through there because it's a path of least resistance. In terms of voltage, this voltage right here is going to change because the parallel combination of 1K and 10 ohms would mean a equivalent resistance of less than 10. And REQ would be less than 10. So voltage division principle from here would be Vx is equal to 20 times 1000 divided by 4000. But now my Vx would be 20 times approximately 10, or actually less than 10, would be 9 point something divided by 3010. So my Vx is not 5 volts anymore because my load value has changed. Does everybody see that? Let's take a 10-second pause while you think over that and let me know if you have any questions. Does the example make sense so far, thus far? Without any load connected, our voltage divider network would give us 5 volts at the output. Vx would be 5 volts. We plug in a load of 10 ohms to the output. Vx has now changed. The voltage across that load would be less than 1 volt. It won't be 5 volts anymore. Does everyone see that? So in order to prevent that, to alleviate that effect, we connect the output to a isolation amplifier or voltage follower. And V out would stay at 5 volts. RL could be any value. It'll still stay at 5 volts. It isolates the load from your supply voltages, or isolates two different circuits so that avoid loading effect. OpAmp has the property of very high input impedance and very low output impedance. And because it has low output impedance, the output voltage would not change, remain constant. If you apply 5 volts to this circuit, you would receive 5 volts at the output. And you can try that in the lab. So this is the first circuit. Just an explanation for one of the most popular applications of an op-amp. The analysis steps for a inverting circuit are listed here. First step would be to verify whether negative feedback is present. Negative feedback means the output should have a pathway back to the input. That's negative feedback. Okay, negative feedback. So if output is fed back to the input, we are forcing V in to go to 0. Okay, real life, it's as close to 0 as possible. So we are forcing V in to go to 0. So the assumption for our analysis would be that V in goes to 0. And because V in into the op amp is going to 0, IN is also forced to 0. And again, remember the concept of the op amp where the input current going into the op amp is 0. Virtual short and virtual open at the same time. Current going into the op amp between the input terminals is equal to 0. And then you can apply your analysis techniques to determine the output. Analysis techniques would be KCL, KVL, and Ohm's law. Okay. All right, inverting amplifier. So we have an op amp. Inverting amplifier means our input is being applied or connected to the inverting terminal. Our output is connected back into the inverting terminal. So negative feedback is present. So that's the first step. Negative feedback is present. And then we have two resistors, input path, and then in the feedback path, R2. Some circuits, some books, R1 is referred to as R in, and R2 is referred to the feedback resistor RF. Okay, the in stands for input, and the F stands for feedback. So several books and several authors would have different notations. RF and R in are by far the most common ones. Okay. Sometimes it's RI also. I again stands for input. So let's look at the non-inverting terminal. Non-inverting terminal goes straight to ground. Okay. This is the voltage at the inverting terminal. This is the voltage at the non-inverting terminal. Vx is equal to V plus minus V minus. Inverting, non-inverting voltage minus the inverting voltage. So we have V plus minus V minus. Now, V plus is connected to ground. Value is 0 volts. Virtual short concept. We can write V minus is equal to V plus is equal to 0 volts. So non-inverting input is connected to ground. So we can say the inverting terminal is also virtually connected to ground. V minus is also at 0 volts. This is the current that's going in. It should be I minus. This is the current that's coming from the supply. And this is the current in the feedback path. Sticking with the naming convention, I can write I1 and I2. Okay, I1 and I2. Also note the power supply voltages, VCC and VEE, are not shown. They're just implied. Okay. Let's take a pause and just reflect on the steps that are shown here. Yes. No. Well, yes and no. Question being asked is basically why and how is V in considered to be 0? Because of negative feedback. So V out is connected, a portion of V out is, so V out is connected to V in, a portion of V out is fed back into the input. So if it's being fed back into the inverting terminal, the cumulative effect is that you have V in coming into the non-inverting terminal and the output is fed back into the inverting, so it's being decreased. And so it's forced to go to 0. And V in is the difference between the inverting and the non-inverting terminals. V in would be the difference. The actual signal could be something else, but V in for the op-amp is the difference between the two terminals. And so that is being forced to 0. Okay. So in this circuit, non-inverting terminal is connected to ground. By the virtual short concept, we can say inverting terminal is also virtually connected to ground. Because it's virtually connected to ground, V minus and V plus are both 0. So if you apply KCL at the inverting terminal, we can say there is no current going into the op-amp. I minus would be equal to 0, right? If I minus is 0, KCL is I1 is I minus plus I2. And therefore, I1 is equal to I2. All of that current is flowing through the feedback resistor. If it's flowing through the feedback resistor, I can write the expression for I1 and I2 in terms of the node voltages. For I1, that's the current flowing through R1. So that becomes V in minus of V in minus of V minus divided by R1 is equal to V minus minus of VO, the output voltage, divided by R2. Those are the two resistors and the currents flowing through those two resistors. If I rearrange the terms to obtain an expression for V out over V in, this is what I would obtain. V out over V in is minus R2 over R1. Because V minus is equal to 0. If V minus is equal to 0 and you rearrange the terms, you obtain V out over V in is minus R2 over R1. V out over V in is the ratio of the output voltage to the input voltage. That means it's the voltage gain expression. And that is the small derivation of the voltage gain for a inverting amplifier. The minus sign indicates it's 180 degrees out of phase and it's an inverting configuration. So by choosing the values of R2 and R1, we can design a inverting amplifier with a specific gain. If we choose a ratio of 10, we can have a gain of 10. If you apply 1 volt at the input, you get 10 volts at the output. If you apply 10 volts at the output, you get, how much would you get? No, if it's a gain of 10 and you apply 10 volts at the input, what would be the output? 100. If you apply 100 volts, how much would you get? Okay, technically that answer is correct, but where is that energy coming from? I'm asking everyone. It comes from the power supply voltages. So the important point that I'm trying to make here is that the output of a op-amp, or any circuit for that matter, cannot exceed the supply voltages. If the supply voltage max is plus minus 10 volts, your output cannot increase beyond those limits. If your supply voltage is 100 volts, your output cannot exceed 100 volts. If your supply voltage is 1000 volts, and get 1000 volts. So all of the energy in the circuit is contained and cannot exceed the supply voltages. So even if the AC signal, let's say you apply 10 volts, plus minus 10 volts. Okay, so the maximum swing would be minus 10 to plus 10. If you have a gain of 100 in your circuit and you apply 1 volt, right, 1 volt AC signal, your output is going to clip at 10 volts, plus minus 10 volts. Okay, it's going to saturate at the power supply level. All right, let's take a pause. Let me know if you have any questions. Okay. So if we add one more resistor to the inverting terminal, we can apply 2 inputs. If we add one more, then we can apply 3 inputs, and so on and so forth. And thus, we obtain something known as a summing amplifier. So this performs the operation of addition. Okay, summing amplifier performs the mathematical operation of addition. By its very definition, it is a differential amplifier. It amplifies the difference between any two signals. This is a summation of 2 or more signals. So in this example, we are applying 2 voltages, VA and VB, to the inverting terminal. And the resulting output, VO, would be an amplified sum of VA and VB. Okay, so V out or VO is an amplified sum or summation of input signals. Okay. The analysis is not too different from what we just did previously. If we have two inputs or three inputs or four inputs, each one of them has a current flowing through. So we have IA, IB. If we had a third one, let's say VC, we could have a third current IC. Once again, V plus is equal to 0. So I minus and V minus is also equal to 0. You have IF, the feedback. And if you apply KCL, like KCL at the inverting terminal, we obtain IA plus IB plus IC is equal to IF. You can apply Ohm's law. We can write VA over RA plus VB over RB plus VC over RC is equal to IF. IF would be 0 minus V out over RF. Okay. We rearrange the terms. VO is equal to minus RF over RA times VA plus RF over RB times VB plus RF over RC times VC. Okay. If you choose all resistor values to be the same, RA, RB, and RC are equal, meaning every single input that's coming is amplified in equal amounts, then the result is a sum of the input signals. If we wish each signal to be amplified by different amounts, we just keep the values different. Then each individual signal would have a different gain. The result is that all the voltages at the input terminals are summed up. And so the output would be VA plus VB plus VC plus VD plus VE plus VF, depending on how many inputs we want to give. It's as straightforward as simply connecting all of them in parallel, not in parallel, but all of them together at one endpoint to the inverting terminal. Okay. All right, let's take a pause. Let me know if you have any questions. Inverting amplifier and non-inverting. How many of you have finished this lab in 361? All done. You did a summation of the signals in the lab too. Did it work? What do you mean, kind of? Oh, okay. Oh, okay. But it worked. Okay. Uh, yeah, that's the OpAmp, yes. There are several other functions that we can perform with the OpAmp. So I'm going to go through with the non-inverting amplifier. There is again a derivation. So let's go through there. This is a summing amplifier. This is another example of an inverting amplifier. Having more resistors in the feedback loop, we can change the equations, and we can have a more we can have more control over our gain. Okay, with a single resistor in series, it's a simple circuit with simply RF divided by R in. With using multiple resistors, we can have any value of the gain. Okay, we are not simply restricted to the value of the resistors. So this derivation will come back. I'll come back to this later. For now, I want to get into non-inverting amplifier and the other couple of circuits. So in the non-inverting amplifier, the output is now fed back to the input. The signal is not applied to the inverting terminal. We're applying it to the non-inverting terminal. So a signal is being applied to V plus, not to V minus. The other components remain the same. We have negative feedback. So R2 or RF is right here. And then you also have a resistor that connects it to ground. Okay. Okay, so negative feedback, check. And thus VI is equal to 0. And that also means II going into the op-amp is also 0. Okay. And V in is equal to 1. The output and feedback loop are right here. Okay. This is ground. That means that these two, actually all three of these are connected together. So let's do it this way. All of these are connected together. And so the output we have something like this. This is RL, this plus minus VO. This is R2, and this is R1. Okay, VO is dropped directly across R2 and R1 in series. Okay, so this is VI right here. VI is because of the virtual short concept. If you apply V in at the non-inverting terminal, we also say it's the same as the inverting terminal. Again, virtual short concept. So if it's the same, I can write V in is equal to VO times R1 over R1 plus R2. Simple voltage division. Right? Voltage across at this point will also be equal to V in. And so it will be VO times R1 over R1 plus R2. If we rearrange the terms, it becomes R1 plus R2 over R1, which becomes 1 plus R2 over R1. So the gain of a non-inverting amplifier is 1 plus R2 over R1. We're applying V in to the non-inverting terminal. Due to the virtual short concept, we can state that the voltage at the non-inverting terminal is the same as the inverting terminal. The inverting terminal has a resistor R1 connected to ground. And so we can state the voltage across R1, which is right here, is equal to V in, which is this. Okay. VI. And then from voltage division, we can write that is equal to VO times R1 over R1 plus R2. Rearrange the terms to obtain an expression for V out over V in, and we get 1 plus R2 over R1. Any questions? In the exam, I'm not going to ask, like in an exam or a quiz, I'm not going to ask you to derive these. These are basically for explanation purposes, okay? The homework problems will have, I think there's one derivation with multiple resistors, which is on the previous circuit, which I'll not enough time to get through today, which I'll cover on Friday. What I'm going to do is for the previous circuit right here, oh, sorry, this one, I'm going to have my annotations on here. And so students can read ahead of class on Friday, and then I can answer any questions. I'll go over the steps on Friday, but the analysis is a little bit longer. So I'm going to write the annotations outside of class. Okay, so on Friday we can go through those. But again, get started on the homework. And this also I'll perform outside of class. What kind of circuit is this? Inverting terminal is grounded. Inputs are going into the non-inverting terminal. So it's a non-inverting amplifier, and you have multiple inputs, VA, VB, going into one single terminal. So it is a summing amplifier. So it's a non-inverting summing amplifier. Okay, similar to the inverting summing amplifier. So the function remains the same. The equation would be slightly different. The gain would be 1 plus R2 over R in. The inputs would be, the output would be a summation of VA, VB, and VC, VD. Okay. Let's see. I want to talk about active filters. So let's do that. All right, active filters. One of the more popular applications for an op-amp is to use it as a filter circuit. So if you remember chapter 6 from E201, filtering components of filtering capabilities of capacitors and inductors. You had a passive filter, which looked like this. Anyone remember? What kind of filter is this? Low pass or high pass? You can use ideal diode analysis for this. Capacitor impedance is 1 over omega C, 1 over j omega C. As the frequency increases, impedance decreases. As the frequency decreases, impedance increases. So at low frequencies, capacitor behaves like an open circuit. So at low frequencies, this is 1 over 2 pi fc. So at low frequencies, ZC is high. And F is equal to 0, meaning DC, capacitor behaves like an open circuit. At high frequencies, ZC is low. At very high frequencies, capacitor behaves like a short circuit. So this one right here, sorry, not ideal diode analysis. What am I saying? This previous class was ideal diodes. At low frequencies, since capacitor is open, V out is equal to V in. And at high frequencies, capacitor behaves like a short circuit. So V out is equal to 0. So low frequencies are allowed to pass through to the output. High frequencies are blocked. Hence, it is a low pass filter, LPF. A quick recap of EE201. Low pass filter, okay? But this is a passive low pass filter, meaning it doesn't do any amplification or attenuation on the input, okay? What is V out is simply dependent on V in. Now, if you wish to connect, if we connect the same capacitor circuit to an op-amp circuit, we can now provide some amplification to our input signal, okay? So these are known as active filters. Active filters. So if you were to analyze this, at high frequencies, meaning when F tends towards infinity, F tends towards infinity, capacitor is a short circuit. So the op amp looks like this. What happens then? What happens to V out? Virtual short concept. If positive terminal is connected to ground, the inverting terminal also is virtually connected to ground. So at high frequencies, the output of the op amp goes to 0 volts. At high frequencies, at low frequencies, F value tends towards 0 hertz. Capacitor is open circuit. Op amp behaves like a normal inverting amplifier. V out is equal to V in, or appropriately AV times V in. So this behaves like a low pass filter. Low frequencies are allowed to pass through the output. High frequencies are shorted out or blocked. So this op amp works as a active low pass filter. It filters out and it provides some gain. Okay, filters out and it provides some gain. And we're almost out of time. This is analyzing the circuit in the frequency domains. In the frequency domain, the circuit is a filter. In the time domain, this circuit behaves like an integrator. Capacitor voltage, V, is 1 over C integral of the current I. Capacitor current I is C dV over dt. Integrate both sides, you obtain expression for capacitor voltage. Integral between time 0 and t, IC dt. And so V out is an integral of the input voltage V in. So when you analyze in the time domain, the circuit works like an integrator. If you apply a sine wave to it, you'd obtain a cosine waveform at the output. If you apply a square wave, you will obtain a triangular wave at the output. So if you vary the frequency, it works as a filter. If you simply apply a single input frequency and analyze in the time domain, you obtain an integral of the input. So mathematically, it works as an integrator. All right, we are out of time, so I'm going to end class right here. We'll pick up here again on Friday. There's, let's see, there's high pass and cascaded band pass. We'll take a look at it next class.